Across the Dardanelles, a massive bridge stretches between two continents, carrying a roadway across a gap that seems almost impossible to span. But building this crossing wasn't simply a matter of connecting two towers. Engineers had to work above deep water, handle enormous structural loads, and assemble the bridge piece by piece. So how do you build a crossing this massive when the ground you need to build on is far below the water? The answer lies in a carefully engineered sequence, from the foundations and towers to the cables and the final roadway suspended between them. And every stage had to work perfectly. The first challenge was the water itself. A bridge like this cannot simply be built from one side and extended toward the other. The structure has to carry its own weight, resist wind and movement, and remain stable while enormous forces are transferred through the towers, cables, and deck. And that creates a very different problem from building a road on solid ground. On land, engineers can bring heavy equipment directly to the work area. Over open water, every major operation becomes a coordination problem. Where do you place the foundations? How do you build massive towers above them? And once those towers are standing, how do you connect them with a roadway without allowing the structure to become unstable? Those questions determine almost everything that comes next. The answer begins below the bridge. Before the roadway can carry traffic, the forces from the entire structure have to be transferred safely into the ground. For a suspension bridge, that means the foundations and supporting structures have a critical job. They have to handle enormous loads while remaining stable in a constantly changing environment. And this is where the project becomes a sequence rather than a single construction task. The engineers cannot simply build the top first. Every stage depends on the stage beneath it. The foundations have to support the towers. The towers have to support the cable system. And the cable system ultimately supports the roadway. So before the bridge could become the dramatic structure visible from the air, the most important work was happening, where much of it could barely be seen. Once the supporting foundations were ready, the next challenge was to rise above the water. The bridge's towers are not just visual landmarks. They are part of the primary load-carrying system. Their job is to transfer forces from the suspension cables down into the foundations. That sounds straightforward. It isn't. As a tower becomes taller, construction becomes more sensitive to wind, alignment, temporary loads, and the weight of the equipment being used to build it. And there is another problem. The two towers have to work together as one system. Even a massive bridge is still a carefully balanced structure. The geometry has to be controlled throughout construction, because the final shape depends on how every major component interacts with the others. That makes precision just as important as size. Then comes one of the most recognizable parts of the bridge, the suspension system. Instead of supporting the roadway entirely from below, a suspension bridge transfers much of the load upward into its main cables. The roadway hangs from those cables through vertical connections, while the main cables carry the forces toward the towers and the rest of the supporting system. This changes the construction problem completely. The engineers are no longer just building a road. They are assembling a large structural system whose components have to work together. And once the cables are in place, another question appears. How do you install a huge roadway over open water without simply putting the entire structure on temporary supports? That is where the construction sequence becomes critical. The deck has to become part of the suspension system while construction is still underway. Each section adds weight. Each new connection changes the forces inside the structure. And the bridge has to remain within its design geometry as the process moves forward. This is why mega-project construction is rarely about one spectacular machine doing one impossible job. It is about controlling thousands of smaller operations so that the structure gradually reaches its final form. A section is positioned. It is secured. The loads change. The structure responds. Then the next section can be added. Step by step, the empty space between the towers begins to disappear. But the final challenge is not simply completing the physical connection. A bridge can look finished long before it is ready to carry traffic. The structure still has to perform as a complete system. The deck, Cables, towers, foundations, and connections all have to work together under changing loads and environmental conditions. Wind matters, traffic matters, temperature matters, and the structure has to accommodate movement rather than simply trying to eliminate it. That is one of the key ideas behind large suspension bridges. They are designed to move within controlled limits. The goal is not to make the bridge completely rigid. The goal is to make it strong, predictable, and stable while allowing the structure to respond to the forces acting on it. And that brings us back to the question behind the entire project. How do engineers create a massive crossing over the Dardanelles? Not by solving one impossible problem with one extraordinary machine. They solve it as a chain of engineering problems. First, create stable support. Then raise the towers. Then establish the suspension system. Then bring the roadway into the structure. And finally, make every component work together as one bridge. What looks from a distance like one enormous object is actually the result of thousands of controlled decisions made in the right order. That is the real engineering achievement of a mega bridge. The final crossing may look simple. 2 shores, 1 roadway. But getting from the first foundation to that finished span requires an entire structural system to come together, piece by piece. If you enjoy seeing how the world's most ambitious engineering projects are actually built, subscribe, because there's always another impossible structure waiting to be explained.